Welcome back everyone. In this lecture we will actually talk about complete reducibility of finite groups. Okay, so first as an example let us see how this complete reducibility works for cyclic groups. So let us start with a finite cyclic group. So let us call it Z modulo NZ. So the order of the group is n, and we know that this group is generated by, let us say, 1 bar, and then all other elements are given by this congruence classes modulo n. So maybe I will use m bar, where m runs over from 0 to n minus 1. So what is m bar? So m bar is nothing but you take this coset corresponding to m. So this is our group. So now we are interested in actually understanding finite dimensional representations of these cyclic groups. So let us take like representation. So let us call it V. So let us say rho is representation of this G modulo NZ. So where the dimension of V is indeed finite. Okay. So let us call it M. So maybe I will use some other notation, maybe capital. Actually it is immediate that even if we work with general finite groups, so any element of that finite group, that when it acts on finite dimensional vector space, so that action must be diagonalizable action. So that is because if we actually take let us say some phi, which is a representation of capital G acting on this finite dimensional vector space V, then this phi of G this is actually satisfies the equation that phi of G power some k is going to be identity on V. So that is because any element of the group G, so that must have finite order. So in particularly, so G power k is going to be identity inside your G. So this is one relation that is given by Lagrange's theorem. So that means the same relation must satisfy by the image phi of G. So we must have this phi of G power k equal to identity inside your GLV. So that means the minimal polynomial of this phi of G, that is going to divide the polynomial x power k minus 1. So the minimal polynomial of this phi of G divides this x power k minus 1. So now once we know that, so that means the minimal polynomial of phi of G. So this minimal polynomial, let us denote it by m phi of G of x. So this is the minimal polynomial. So this has distinct roots. So that is for sure. Since this has distinct roots, so that would immediately imply that this phi of G is diagonalizable. Okay, I guess yeah. So that means it is an immediate lemma that says if we start with a group representation of a finite group acting on a finite dimensional vector space. So both group as well as the dimension is finite. So in this case we can immediately conclude that phi of G is diagonalizable for all G in G. Okay, so this is there for us. So that means in particularly a representation of this Z modulo NZ. So, that also like going to be all the images of elements of this Z modulo NZ will going to be diagnosable. But since we are working with the abelian group, because Z modulo NZ is being cyclic, that implies abelian. So, that means this phi of G, where G in Z modulo NZ, these are all commuting diagnosable operators. So, these are family of commuting diagnosable operators. But anyway, since we are working with actually cyclic group, it is easy to see that the cyclic group is generated by 1 bar. So, in particularly any other element like m bar is going to be just 1 bar sum of m times. So, because of this you can easily see that phi of m bar is going to be just power of this 1 bar m times. Okay. So, now since this phi of 1 bar is indeed diagnosable, just we can use that information to conclude that phi of m bar is diagnosable. So, let us say there is a basis B, there is a basis of V such that this phi of 1 bar with respect to that basis is diagonal. So, let us call it lambda 1 etcetera lambda. So, I guess I used capital N. So, now you have this basis, with respect to that basis we got this diagonal matrix lambda 1 etcetera lambda n, and it is not hard to prove that the same basis actually works for all other operators phi of m bar. So, it is easy to see that this phi of m bar, which is just the power of this phi 1 bar power m. So, this is again the matrix of this with respect to the same basis is going to look like lambda 1 power m etcetera lambda n power m. So, what does it mean? So, we got one single basis for which all the elements of this phi of m bar, they are all simultaneously diagonalized. So, for the same basis B, this phi of m bar, all of them are actually simultaneously diagonal. And of course, this is actually easy to prove in this cyclic group situation. This requires little bit involved proof for abelian groups. Maybe I will state here that result and leave it as exercise. It is a very simple exercise. So, the exercise that says that if you have a family of operators which are actually mutually commuting operators that are diagnosable. So, let us say you have a family of operators acting on a 5-dimensional space, that is very important. So, let us say V is 5-dimensional and you have family satisfying the following conditions. Satisfying, first condition is that all elements of A, they are all diagnosable. So, all T in A are diagnosable. And the second condition is that they all mutually commute. So, T s is same as S t for all S t in A. If these two conditions are there, then from this one can conclude that there exists a common basis of your space. So, let us call it V, such that all these matrices of this B, that will be diagonal. So, they all or diagonal. So, if you have a commuting mutually commuting family of diagonalizable operators, then we will be able to diagonalize them simultaneously with respect to one basis. So, that is what this exercise says. So, from this exercise one can immediately conclude that if G is an abelian group and rho is indeed a representation of G, so then there exists a basis B of capital V such that all the elements rho G with respect to capital B, they are all diagonal. So, that means we can simultaneously diagonalize all the images of capital G. So, that is immediate corollary of what we have actually had before. But for cyclic groups that just comes from the fact that any element can be actually generated using the cyclic element, cyclic generator 1 bar. So, this actually comes for free. So, now we can see that so once we have this basis, so let us label that basis as V 1 etcetera V n. Then it is immediate that these subspaces V I which are spanned by this small V I. So, these are all actually Z modulo n Z invariant. So, this is immediate. So, in particularly V can be decomposed as V 1 direct sum etcetera direct sum V n. So, each one of them are one dimensional sub representations, in particularly they are irreducible representation, and we could actually decompose this given capital V as a direct sum of these one dimensional representations. So, we started with a finite dimensional representation of this cyclic group, and then we could immediately see that using the action of this row of 1 bar. So, that is good enough, and then we constructed a basis, and with respect to that basis we actually got this matrix row of 1 bar with respect to B as a diagonal matrix. So, now given this information we could actually get the decomposition of V into irreducible factors, where V I is just a span of small V I and this V I comes from capital B. Now, if you think about it, these lambda i's, so they are actually not some random complex number, since order of 1 bar is n. So, we must have row of 1 bar power n is equal to identity. So, that means the minimal polynomial of our matrix row of 1 bar. So, that actually must divide this polynomial x n minus 1. So, that means all this lambda 1 etcetera lambda n, they are all actually nth roots of unity. So, all these lambda i's are nth roots of unity. So, in particularly if we go back to the representation that we constructed earlier. So, this rho k, if we recall this is actually representation, one dimensional representation of this Z modulo n Z. So, which is given by sending 1 bar to this e power 2 pi I k divided by n. So, now we know that Z modulo n Z has this presentation which is generated by one element with the relation that a power n equal to identity. Using that it is easy to verify. So, this actually defines representation. Now, so this rho k, they are all actually one dimensional representations of Z modulo n Z. So, these are all irreducible, of course, one dimensional representations of Z modulo NZ. So, now what is the relations between this rho k and this V I? We can easily see that these V I's are nothing but isomorphic to this rho k i's. Since this lambda I is actually belongs to this nth roots of unity. So, that means this lambda I is supposed to be equal to one of this 2 pi I k divided by n. Okay. So, maybe like let me put it that. So, there exists k I such that, so this lambda I is nothing but e power 2 pi I k divided by n. So, that means this V I that we constructed is naturally isomorphic to the representation this rho k, C star rho k I. Maybe you can take it as exercise that all these rho k are actually inequivalent representations. So, maybe I will write it here. So, this rho k where k comes from 0 to n minus 1. So, these are actually inequivalent irreducible representations of Z modulo n. So, and we just proved that any finite dimensional representation of Z modulo n Z will be isomorphic to direct sum of these rho k's with some multiplicities. So, this indeed proves that any finite dimensional representation of this Z modulo n Z must be completely reducible. Okay. So, this is something very easy to prove for representations of cyclic groups. So, now let us see how one can actually approach this question for the general finite groups. Of course, we had lots of information about the finite cyclic group. So, that is why it was somewhat easier to prove. Indeed, the exercise that I actually gave before, that any family of commuting diagonalizable operators must be simultaneously diagonalized. Using that exercise, one will be able to prove similar result even for the finite abelian groups. Okay. But how do we generalize that to general finite groups? So, that is indeed a real task. So, we will see that we can use some ideas from actually linear algebra in order to do this. So, let us recall the most important fact that actually we had it in the linear algebra. So, if we actually work with the inner product space, so we always actually could spot complement of any subspace uniquely. So, if W is a subspace of V and let us say V is given inner product space. So, then there are of course infinitely many choices for the complement of W, but using the inner product on V. So, we could actually pick a unique choice for the complement. So, that is the orthogonal complement of W. This is those V in V such that the inner product V comma W is 0 for all W in W, and this gave us unique way to choose orthogonal complement. But how do we actually make sure that existence of this orthogonal complement gives us actually complement of G sub representations? So, indeed to do that, so we are going to actually start with some general abstract finite dimensional representation. Somehow we need to actually impose some inner product on that, so that that inner product actually becomes G invariant. Once we make sure that, then given any subspace we will be able to take its orthogonal complement, and that is going to give us the complement subrepresentation that we are looking for. So, here is the idea. So, maybe let me just simply write it down. So, let us say V comma rho is given representation of V, representation of G. So, this is again finite dimensional representation. So, now what we do, so we randomly pick some inner product on V. So, randomly pick an inner product on V. So, now this random inner product may not helpful. So, what we do, we use this averaging technique. So, there is this averaging trick. So, that actually help us to average the inner product, and that will, using this averaging trick, we will actually get what is called G invariant inner product. So, we get G invariant inner product. So, once we have this G invariant inner product, then given any W, so given any W sub representation, so we can make this unique choice of orthogonal complement of that, which will be inside V, and we will be able to prove that this unique choice of orthogonal complement of W. So, that is going to be again sub representation, again sub representation of V, and not only that, and that is going to be a complement of W inside V, because that is anyway comes from the linear algebra. So, in particularly we will be able to actually write V as W direct sum W perp. So, now in order to prove complete reducibility, so we need to make sure that V is completely reduced into direct sum of irreducible representations. So, for that what we can do, we can use the idea that we actually explored before to complete that complete reducibility. So, all we need to do is, like, if the representation that we started with is already irreducible, then there will be nothing to prove, because that is already direct sum of irreducible. Then if it is not irreducible, then we can make sure that there will be a sub representation W, non-zero proper sub representation of this given V. So, let us call it W. Then using the earlier ideas, we will have this complement of that W. So, now using induction, we will be able to actually decompose this W into direct sum of irreducibles, and similarly this W perp also using induction will be direct sum of irreducibles. So, then putting them all this is irreducible sums together, we will be able to say that V is indeed direct sum of irreducibles. So, this is how one can prove complete reducibility for the finite groups. So, the main idea is this averaging trick. Okay, so, let us see how one actually do that. So, for that purpose, let us first actually define some terminologies, so which will be useful later to understand what we are trying to do. So, here is the first definition, the definition of unitary representation. So, what is an unitary representation? So, we start with the, let us say, inner product space V, and then assume that we have the action of the group on this inner product space G. So, then, so that means it is a representation. So, that representation rho is actually called unitary if all the images of this G, so that means rho G, they all live inside this unitary group UV. So, that means this rho G is unitary for all G in G. So, that means rho of G is unitary operator for all G in G. So, in terms of the inner product, what does it mean? So, if we take this inner product rho G V and then rho G W. So, this inner product is going to be same as the inner product V W. So, that means the operator rho G preserves the inner product that we have it on the space capital V. So, this is true for all V W in capital V. So, now once we have this unitary representations, we will be say much about that. So, what we can prove, so let me state it as a proportion. So, any unitary representation, it is either irreducible or it must be decomposable. So, let us say phi is unitary, so then we can conclude that either phi is either irreducible or decomposable. So, how do we prove this? So, if we to begin with, if V is irreducible, then there is nothing to prove. So, assume that V is not reducible. So, here is the proof. So, assume that V is not irreducible. So, then we want to prove that it is decomposable. So, now because it is not irreducible, so there exists a non-zero proper sub-representation, let us call it W. So, then immediately one can define the orthogonal complement of W. So, let us call it W perp, which is defined to be those vector which are orthogonal to all elements of capital W. So, now it is easy to see as a vector space that V is nothing but W direct sum W perp. So, we claim that this W perp is indeed sub-representation, it is indeed sub-representation of capital V. So, once we prove this claim, then it is immediate that the space that we started with decompose, the representation that we started with decomposes as W and W perp. Since W is proper, so it is immediate that this complement W perp is also non-zero sub-representation. So, let us verify it is indeed sub-representation. So, for that purpose, let some vector V in W perp and then some element G in G, then let us compute what happens to G dot V. So, G dot V is same as rho G V. Okay. Let us simplify the notation. So, if we compute G dot V comma W, the inner product, then it is immediately true that since this inner product is G invariant. So, G inverse dot G dot V is going to be same as the inner product of G dot V comma W will be same as this inner product, because we are working with the unitary representation. So, this is supposed to happen. So, this is going to be equal to G inverse G dot V comma G inverse dot W, which is exactly equal to, so this is identity acting on V. So, this is V and then this is exactly G inverse dot W. Since V is coming from W perp and G is coming from capital G and this W for any W in W, that is what we are computing. So, you can see that this part must be equal to 0 as V is in W perp. So, that implies that this G dot V comma W is equal to 0 for all W in W. So, that implies that this G dot V must be an element inside your W perp. So, this proves that W perp must be a sub representation of capital V. So, this is a sub representation. So, that means V decomposed as two non-trivial representations. So, it must be decomposable. And this also indeed proves that by induction, now using the induction on the dimension. So, you can easily prove that this can be further factorized into direct sum of irreducible unitary representations. Again, this is also again further decomposed as direct sum of unitary representation. So, for which you can take the inner product restricted to W and W perp, that will make both W and W perp will be inner product spaces, and the action of G on V restricted to both W and W perp will be again unitary. So, that those things are easy to check. So, by checking them you can easily prove that any unitary representation is indeed direct sum of irreducible unitary representations. But now the task is how do we actually start with some general representation, and then from that how to make that as a unitary representation. So, that is what we need to do in order to complete the complete reducibility. So, maybe I will stop here and then I will do that in the next class. Thank you.